Quizlet from today, and we have to sketch and we have to find derivatives here. And the sketching always happens with a three-point solution. In particular, for both of these graphs, I'm going to find 3 points that I know on the graph of y equals sine x, and I'm going to sketch the inverse on a region of sine x that always has the same sign of derivative, in this case always increasing. And so if I sketch a little portion of y equals sine x like so, then I can see that the 3 points that I have here are negative pi over 2, negative 1, 0, 0, and pi over 2, comma 1. These now become this function we call y equals capital S sine x. It is an invertible version or branch of sine. And so now, if I invert these points, I get negative 1, negative pi over 2, 0, 0, and 1 pi over 2. And I'm going to draw it so that it is also increasing, but so that my horizontal tangents here become vertical tangents. And here's the graph of inverse sine. Not hard to do. For inverse tangent, and let me pull this down and make it in a different color. We're going to do the same kind of thing. We're going to choose a branch of tangent, or a piece of tangent is a better way of putting it. For which tangent is always increasing, like so. And so our 3 points are really the two vertical asymptotes here and the origin. And so that immediately gives us two horizontal asymptotes for inverse tangent and the origin. And now my graph looks like so. So that's how the graphs go. Now how about the derivatives? The derivatives are going to happen either by using inverse function or by simply inverting like so. And now I can take a derivative with respect to x on both sides, so that dy dx is equal to 1 over cosine y. And as we saw yesterday, we can use the Pythagorean theorem to rewrite cosine y as root 1 minus sine squared y. And the last key insight, sine y is x. Just like so. As far as that goes, if you have a good proof, 1 point. If you have a good graph, 1 point. Down here, same process. And y is equal to x, so secant squared y dy dx, y prime is equal to 1. And now we appeal to the Pythagorean identity that secant squared y is the same as 1 plus tan squared y, and tan y is equal to x. So again, a good proof is worth 1, and a good graph is worth 1. Mark them up out of 4, and pass them up. Yeah, so he did follow the average. Yeah. Here there's a typo. I think we'll let it slide, but notice you have root 1 minus x instead of 1 minus x squared. But you had sine squared y here. Be careful with that notation though. This doesn't mean the same thing.
Oh, this should be 10 squared.
Yes, right. Tan y squared, when you take y squared and get the tangent of that. Okay. Now, I want to do two things. One is I want to talk about the use of right triangles to help resolve things. And the other is I want to talk about our inverse secant, cotangent, and cosecant. This is what I meant to write. So that's our agenda for today, and I want to do it in kind of a funny order. First, I'm going to talk about secant, inverse secant, and cosecant because they're fairly easy. Then we're going to do right triangle analysis, and then we're going to come back and do the inverse cotangent last. Okay? So as far as inverse secant and inverse cosecant go, the trick about inverse secant is that it has these vertical asymptotes at x equals pi over 2 and x equals negative pi over 2, and in general x equals 2k plus 1 pi over 2. And if you take a look at the graph closely, because secant x is 1 over cosine x, the graph is going to look like this, which I affectionately call horseshoes. Each piece looks like a horseshoe, right? And the trick about the horseshoes is that they are not monotonic. They don't have the same sign of derivative all the way through. And so to fix that, we have to awkwardly do this. We're going to choose this piece right here combined with this piece right here so that we get a one-to-one function. So the part that we're going to invert is the part that has always positive slope, right there. And now when I invert it, what I get for inverse secant is a horizontal asymptote y equals pi over 2. So there's one point. And then a second point is going to be the point 0, 1, which turns into the point 1, 0. And then my graph approaches the asymptote like so. And then my third point is going to be the point pi negative 1, which becomes the point negative 1, pi, and the graph approaches the asymptote like that. Very strange looking graph. But you can see why it works. The domain of my stuff in red here is 0 to pi except for pi over 2. So the range here is 0 to pi except for pi over 2. The range of secant is 1 up and negative 1 down. In other words, 1 to infinity and negative infinity to negative 1. So the domain of inverse secant is negative infinity to negative 1 and 1 to infinity. That make sense? Now when I do the derivative, something gets really interesting. What is the derivative of inverse secant? Well, I do the same procedure that I did before. Yeah. So secant y equals x, and now I get secant y tangent y dy dx equals 1. So the dy dx is equal to 1 over secant y tangent. Now, half of this is easy because secant y is x. The tangent y comes from the Pythagorean identity. Secant squared y equals tan squared y plus 1. So tan squared y equals secant squared y minus 1. So that, here we have an ambiguity.
So x times 2.
Except for one thing, and that is that we have a plus or minus sign. Tan y could be the square root of secant squared minus 1, or it could be the opposite. Which one do I choose? Here's the very interesting thing. If I replace down here, I observe I've got two possibilities. Now I go back to the graph of secant, and I observe that when, yes, whether x is positive or negative, I'm going to have a positive slope. In other words, when x is positive, I want to take the positive root, and when x is negative, I want to take the negative root. Now we know a function that is equal to x when x is positive and opposite x when x is negative. What is that function? Yeah, what is that? It's the absolute value. That's exactly right. So the most concise way to put this, so that we always get positive slope, is that dy dx is 1 over the absolute value of root x squared minus 1. And that absolute value of x is not obvious, but it comes about so that for our particular branch that we chose, we get the right sign of the slope. Does that make sense to everybody? That's the little piece that I didn't want to do yesterday. The same kind of thing happens with cosecant, inverse cosecant. I'm going to have to take so, and my cosecant graph comes down like this, and like this, and like this, and like this, horseshoes again. And so I'm going to have to take a branch that has all one side of derivative, and that branch is going to be across from negative pi over 2 to positive pi over 2. So that y equals inverse cosecant is going to have a horizontal asymptote y equals 0, and it is going to have 2 points, 1 comma pi over 2, and it's going to go out to infinity. It's going to approach the asymptote, and then the matching point, yep. And it's going to approach the asymptote like this. And notice that inverse cosecant always has negative slopes. So it is no surprise that when I do dy dx, I get negative 1 over the absolute value of x root x squared minus 1. Are we good so far?
Yes.
Okay. And what I'd like to do is to talk a little bit about constructing right triangles to represent these inverse trig functions so that we can solve various problems. Now let's take y equals inverse sine of x as an example of this.
Oh, and it's just a question. Not really.
Go ahead.
So you remember the triangles 3, 4, and 5?
Yes,
What did you say the angle was?
you work it out. You've got a calculator in front of you.
Is it like 15?
You work it out.
It was that yesterday.
Okay.
With it here.
Now, here's the way that we want to think about this. The y here represents an angle. It represents an angle. It's an angle whose sine is x. And the x here represents a ratio, a trig ratio, not a ratio. So if I were to set up a right triangle to represent this situation, make it larger and righter. Then my right triangle looks like this. In the corner, I've got an angle of pi over 2, 90 degrees. And here, I have the angle y such that the sine of y is opposite over hypotenuse. And the easiest way to do that is to make the opposite be x and the hypotenuse be 1. This right triangle right here represents the equation y equals inverse sine x.
But it's inverse.
Yes.
It's inverse.
Yeah, it's the inverse. Exactly right. So the virtue of drawing this right triangle is that we see some things. First of all, what we observe is that the other angle is complementary to it. So that I can write the cosine of pi over 2 minus y is also equal to x. Everybody see that? But if I invert both sides, look at what I get. I find out something very interesting. And that is that the inverse sine and the inverse cosine are actually two angles that are always complementary to each other. Ah, that's a nice insight. But what that means is that when I take derivative with respect to x on both sides, when I take the derivative with respect to x on both sides, on this side, I'm going to get 0. And on this side, what I find out is that the derivatives of inverse sine and inverse cosine must be opposites of each other, because the two angles add up to a constant. In other words, specifically, d dx of inverse sine, we already know, is 1 over root 1 minus x squared. d dx of inverse cosine is the opposite of that.
Did you say like inverse cosine x and inverse sine x? They're complementary.
Yes.
Why do we need to prove this as
Well, it's helpful to us because we observe, therefore, that their derivatives are opposite.
pi over 2 already means it's 90 degrees.
Yes.
So why do you further prove this?
You don't.
Oh.
I'm developing that idea. So the idea here is that I can see from the triangle that they are complementary angles.
Yeah.
And then from that, the derivative stuff follows. Specifically, the derivatives are opposites of each other. Okay? So that's right triangle analysis. Now, we could do the same thing for inverse tangent, right? But we're going to have a different relation. And our triangle will look different. If I have y equals inverse tangent of x, then what I'm really saying is that y is an angle whose tangent is x. In other words, the opposite over the adjacent will be equal to tangent. So this triangle represents y equals inverse tan x. And if I now compute the if I now want to consider the inverse cotangent is going to be adjacent over opposite, which means that the inverse tangent and the inverse cotangent are also complementary angles. And I'll bet you can imagine it doesn't take too much work to figure out that the inverse secant and inverse cosecant are complementary angles also. So what this means really is that I really only have 3 inverse trig functions: inverse sine, inverse tangent, and inverse secant. And the other 3 are simply the complements of those 3. Does that make sense, everybody? There's more hidden in these right triangles that's kind of cool. Suppose I have some expression like this. Evaluate the sine of the inverse tangent of x. Ugh. What does that even mean? Well, the right triangle actually makes short work of that. If I take and create for myself a right triangle that represents inverse tangent of x, like so. So I have an angle y whose tangent is x. Then I can evaluate the sine of that angle y by using the Pythagorean theorem to solve for the third side, and then doing opposite over hypotenuse. And I'm done. Isn't that nice? This means, among other things, that I can solve for all sorts of nifty types of relations. For example, if secant theta is equal to 2/3, find sine theta. That looks like a horrible problem. I've got to find an angle, then I've got to find a sine. No, I don't. I can create a right triangle with an angle theta whose secant, that is going to be hypotenuse over adjacent, is equal to 2/3. How about 3/2, since that doesn't make any sense. There we go, much better. Whose hypotenuse over adjacent is equal to 3/2. And now the Pythagorean theorem allows me to find the third side, as we find.
That would be the sine.
And the sine of that angle
Root 5 over 3.
is root 5 over 3. And I never had to find the angle. So the right triangle analysis here is very, very convenient. And physicists especially use it very often. Okay. Now, here's one place, I think I can do this. Here's one place that gets really interesting. What is the relationship between inverse sine and inverse cosecant? Because we know that cosecant of theta is 1 over sine theta. So it seems like there ought to be some kind of relationship between those two. Okay? We can actually answer that question with a right triangle. Let's actually put this question on a new page and use a right triangle to answer. I create for myself a right triangle that represents the inverse sine of x. I'm going to have some angle theta right here, whose sine is x. So this represents theta equals inverse sine of x. And now I'm simply going to ask, what is the relationship between that and inverse cosecant? Well, if I draw myself a right triangle that represents inverse cosecant, then now I need to draw for myself a triangle whose cosecant, an angle whose cosecant is x. And if we take a look at these two, we can see that the relationship is a reciprocal relationship. That the inverse cosecant of x is the same as the inverse sine of 1 over x. Now, if this is hard to see, we could also do it like this. We could solve those sides for sine theta equals x. And we could observe that cosecant theta is equal to 1 over x, so that theta is the inverse cosecant of 1 over x, just like that, or vice versa. So there's an algebraic way to get there, there's a geometric way to get there, and what we find in particular is that these relationships are true. And we expect, therefore, that the inverse cotangent of x should be equal to the inverse tangent of 1 over x also, because the two functions are reciprocals of each other. So notice that the reciprocal relationships are essentially inverted. Okay. Here's where the interesting problem comes in. If I take a look at inverse cotangent, and define it as the inverse tangent of 1 over x, then I'm going to get a particular graph. Here's y equals inverse tangent of x. My graph goes like so. And that's all good. Okay? So if I take the inverse tangent of 1 over x, notice that from here to here, x goes from 0 to infinity, right? So that as x goes out to infinity, 1 over x goes to 0. Yes? And so that means that the limit as x goes to 0 from the right should be pi over 2. And as x goes to 0 here should be the limit as x goes to infinity down here. Does everybody see how I took the branch in the first quadrant and flipped it by doing 1 over x's? Meanwhile, in this quadrant right here, what I'm going to get is the same thing, but inverted, like this. So this gives me one possible graph for the cotangent. Two problems with the graph. One is it's ugly, and B, it doesn't actually exist and is discontinuous, and x equals pi over 2. So it's awkward. It obeys a relationship that I want, but it has some features that I don't like. One more thing. If I define the inverse cotangent as the complementary angle to inverse tangent, like so, I get a different graph because I get a different branch of this function. If I take all of these values and subtract them from pi over 2, then as x goes to infinity, cotangent goes to 0, and it will increase all the way to pi, so that I get a different branch of the relation. Which one is right? It's a matter of definition. Which one is used? Both, depending upon your circumstances. So, I call the inverse cotangent the ugly stepchild because it has this sort of ambiguity about its branches. I can do this, or I can do this. Either way, its derivative is the same thing. dy dx for both of these branches will always be negative 1 over 1 plus x squared. Okay?